Just checking you could actually get out of the building if it catches on fire. So, welcome. As Anna said, my name is James Curran and I'm the head of the Department of Statistics at the University of Auckland. Firstly, I would like to add to Anna's welcome. So, welcome to the University of Auckland, welcome to Teachers' Day. I know but both Anne and Anna have done a fantastic amount of work to make this as interesting and exciting as possible for you today, and I really do hope that you enjoy it. You know, what we want you to take out of this today is just to see that our subject is not static. It is dynamic, it's changing constantly, and there have been some really cool innovations coming out in the last few years, and there'll be many cool innovations in the years to come. So many of you have probably been to this event more than once, and we hope you enjoyed as much as previous times, and we hope that we'll see you again. So I have a job to do, which is to introduce my friend and colleague, Associate Professor Matt Parry from the University of Otago. Matt started his life as a physicist before he saw the light and became a statistician. I think, you know, in terms of that transition, I can't think of another example of somebody who has embraced that change more fully than Matt. If you look at his webpage and if you look at the number of areas that he works in with statistics, it is truly impressive. He makes contributions in epidemiology, in ecology, in genetics, in cosmology, in astronomy. I had to remind myself not to say astrology. And many other methodological areas of statistics. So you won't meet a more comprehensive statistician than Matt. And he still retains his connections to physics. So he has a strong connection to the astrophysics community in New Zealand and the cosmology groups, and makes both physics and statistics contributions there. I understand that Matt is going to talk to you this morning about how he came to love uncertainty. And so I would like you to give Matt a warm welcome to the stage. Thank you.
Morena, ngā mea nui kia koutou. Is that on? Yep. Thank you very much for having me. Thanks to the organisers for letting me talk to you. For me, it's actually a real privilege to be able to have this time, and I'm hoping, I know I'm going to learn probably a lot more from you than you'll learn from me. I'll be staying around for most of the day and looking forward to hearing what you bring as well, because maybe it's an open secret that there's a bit of a disconnect between secondary school statistics education and the tertiary level, except at this esteemed university, actually. This esteemed institution is much better at bridging the gap than maybe some of our other institutions are. So that's why I really want to learn from you today. As James has alluded to, I'm going to talk a little bit about how I stopped worrying, or how I learned to stop worrying and love uncertainty. I'm framing it around my own personal journey. I don't want to make it about me at all, but just that uncertainty is an important thing in statistics, of course, and we need to embrace it. And maybe that's the part I'll tell you about, is how I learned to end up loving it. This is the abstract I gave you. I put it here for future use for myself when I look back at my notes and wonder what I was talking about. The first bit was sort of prompts to me, maybe, to talk about some of the things I've been working on, but I'm probably not going to talk too much about these areas, but that was to get you into it. The guts is really, as I said here, about quantifying uncertainty. If there is a take-home, so I've become a big fan of sort of plain language abstracts and graphical abstracts. I always tell my students, you've got the paper, but just give me a three-liner, which really sums it up for someone who's not an expert. And the picture is even better. So this is what I came up with. I thought here I could distill my whole talk into the following. Statistics refreshes the parts other analyses cannot reach. And this is probably one you should keep to yourselves, maybe not share with your students, but I've got one for them as well. Things go better with stats. And I was very proud of myself, absurdly proud of myself for coming up with these, actually. And then I realized these are about 40 years old, these ad campaigns, so it probably won't mean nothing to all of you, but to old-timers like me, it seemed very clever. Anyway, that's what I came up with. So let's dig into some details. So I guess my aha moment, as James said, I started life as a physicist, not just any physicist, the worst kind, actually, a theoretical physicist, right? So they don't need to worry about things like data. They can just sit around, come up with ideas, and say, wouldn't that be cool? Oh, actually, I'm out of sort. I'm going to give you a teaser, and we're going to come back to this teaser at the end. So here's the thing I want you to think about if you want to zone out at some point during my talk. Which is taller? So on the left, you've got the Eiffel Tower. On the right, you've got the Sky Tower. These are not to scale. But the question for you is, which is taller? And let's add a little bit more to it, a bit of spice. How certain are you about your answer? Okay. So that's what I'll leave that there. We'll leave it hanging, and we'll come back to this at the end. Okay, so as I said, I was doing theoretical physics, and I had a sort of aha moment. So I'm still out of tight sequence. I'm coming to my aha moment. I'm really delaying this. Here's my outline of my talk. Sorry. I changed the slides around at the last minute, so that's kind of why I messed things up. I apologize. We're going to talk about including uncertainty. We're going to talk about propagating uncertainty, and also finally talking about evaluating uncertainty. So those are the key ideas. Okay, here we go. Finally, this is my aha moment. I went to a talk, and the guy said to me, well, not to me, but to everyone, he said, what I want to do is take one of these, look at one of these, measure this, and then estimate these. Okay. It was a very effective start to a talk. So let me take you back to what these things are. This is a multi-billion-dollar satellite that has been launched. It's the Planck satellite. It's out in a special place in space where it can sit. And while it does that, it observes the universe. So this is what it's looking at. This is the universe, or a little snapshot of the universe from another telescope, the Hubble telescope. And what it's trying to measure is the temperature of the sky. And this is the map of the temperature of the sky in a certain frequency band. It's a beautiful picture. So it's a whole sky. It's been sort of wrapped into this sort of oval shape. And what you're seeing through the middle is our Milky Way, actually. So our Milky Way is right bang in the middle of this plot. It messes up the things we care about, really, because what we care about is everything else, away from that band through the middle. But those are little temperatures that have been represented in colours. So blue is slightly colder, red is slightly hotter. The actual change is very, very small. It's about 1 part in 100,000. So we've exaggerated the differences there. But that's what it's trying to measure. And when it can do that, then you can actually end up estimating cosmological parameters. So on the x-axis, you have how much matter, or the proportion of matter in the universe. And on the y-axis, you've got the proportion of what's called dark energy in the universe. And having these measurements allows you to estimate these particular parameters, which are really important. So the ones that in the orange here, you can hopefully see that, this is our estimates of those parameters. And the fact that it's a sort of a big, long orange ellipse, or part of an ellipse, is telling us we're not certain about those parameters. But we're getting, nevertheless, some estimates of those parameters. The other ovals there, you see the blue and the green are different types of measurements people have made with different instruments. And you can see that they sort of overlap in a particular area, and that's our best guess as to what those parameter values take. So I'm not going to talk too much about that, but really what the point of this is, that this is my aha moment. I realized I was messing about doing theoretical physics where people were actually doing some serious stuff, and it turned out to be serious statistics, in order to estimate parameters of the universe, which is, for me, it was just amazing. Well, sort of the penny dropped. Now, the penny dropped, but it took a long, long time for me to actually become a statistician. But there it was, percolating away in the background. Okay, so this is the first topic I want to talk about, is including uncertainty. The other two are propagating uncertainty and then evaluating uncertainty. And there's uncertainty in a number of ways. And I want to confess that I found it really hard to get my head around this stuff. Measurement uncertainty I could understand. We don't measure things accurately, just the nature of our devices that we use. I hated it as a theoretical physicist. I absolutely hated it. I had to do labs, and I hated the labs. And I thought, I did it in high school even, and then we had to propagate uncertainties in our measurements. And I thought that could leave it in high school. Surely we don't do that at university, but they do, of course. So that was one problem. Model uncertainty, I had no idea what this could possibly mean. In theoretical physics, the model is absolutely correct. And if it's wrong, it's because you haven't found the correct model and you spend your time trying to find the correct model. But the idea of model uncertainty, that we don't know everything that is relevant, was anathema to me. Oh, it's really psychologically destabilizing, actually. And then parametric uncertainty, not knowing the parameters or only having finite data to estimate them, maybe I could understand that, but it wasn't what I was thinking about when I was doing physics. So this was stuff that it took me a while to get my head around. So these are the key things. When we talk about uncertainty, and including uncertainty in statistics, it's these three areas in particular, I think, of which are important. Measurement uncertainty, model uncertainty, and parametric uncertainty. And they're all hiding in the cosmological project that I was talking about previously. So probability is the language of uncertainty, so it doesn't surprise you that we're going to talk a little bit about probability today. Okay, here's the modeling framework when we're trying to include uncertainty in what we do. This is a picture, which I hope is helpful. We've got a box, X, which contains the stuff we know. Might be our covariates, our explanatory variables. It could be the state of the world or the universe, if you like, even. It's grand as that. And then we make a measurement. That's our Y. In the blue circle, we have the thing. We care about the outcome of interest. And we're trying to connect the X to the Y, the things we know, to the things we're trying to describe or explain. And connecting them is the orange arrow, which contains some of our parameters. Okay, so that's kind of the framework I want you to have in mind. And when we do linear regression, straight line fitting, we're doing this kind of thing, right? We say, I've got some X's, I've got a Y, and I need to estimate things like slope and intercept and so on. We can, just to say that things like model error included in this, when I talk about what Y is, I'm including model uncertainty. I'm going to try and not use the word error too much because I think it's a bit unfortunate. It sounds like we've made a mistake. What it really means is we're being honest about what we don't know. So model uncertainty and measurement uncertainty are included in this picture. When we talk about how we get Y from X, we're talking about how things like measurement error might come into it or model uncertainty might come into it. But you can actually extend it quite naturally and quite easily. So a lot of my work, I realized, fits into this kind of framework. So we have a series of boxes, a series of things we know, or states of maybe things we don't know actually, but states of the universe, if you like, or covariates, and they may change over time. So we're moving to the right, we're moving forward in time. And so when we talk about our modeling, we're thinking about what's the forward map? How do I go from now to the next time? And each time I do this, I'm also observing the system as well. So each time I get a measurement in that blue circle, or includes the thing I care about. Okay. And prediction then in this setup is just saying what happens next. What's the next box going to look like based on what I've seen in my observations so far? And this is a really powerful framework, and as I say, I use it all the time. It turns out to be really, really useful. So try and keep that in mind. And I'm going to try and now put what my colleague Andrew was telling me about when he was talking about measuring parameters in this context. So this is the cosmology example. We have a Big Bang that happened, and surprisingly, theoretical physicists think they know what happened in the Big Bang. And for context, what I was working on was this little bit right here, just after the Big Bang. That's how I spent my time, right? It's embarrassing to admit to it now, isn't it now? But if we go forward in time, the forward map tells us how we go from the Big Bang to the universe. So now we've moved over to the right here. This is what the universe looks like today. Okay? And then we put this Planck satellite into space and we take a measurement of that universe. And this is the outcome we see, the observations we see in this blue circle, this beautiful map of the temperature of the sky. Okay. So that's sort of the framework. So hopefully now you can see how these frameworks work and how statistics uses them to end up making powerful statements. For time. I want to include one tricky example of measurement uncertainty. And it doesn't follow from what we've been talking about, but it's something I've been working on with a student of mine just recently. And that is, when we think of measurement uncertainty, you're probably typically thinking, oh, I measure the temperature and my device is not very good, it's plus or minus a certain number or whatever. This kind of measurement uncertainty is when we're actually looking at a binary outcome, a 0-1 outcome, and you can't make 0 plus or minus 0.1. Doesn't make sense. It's not 1 plus or minus 0.1. Doesn't make sense. It's either 0 or 1, right? So when you make a mistake here, or you have uncertainty here, you're confusing a 0 with a 1 and a 1 with a 0, right? So it's quite a serious mistake, right? And so I just thought I might mention this. This comes up in the context that we're looking at is trying to come up with a liquid biopsy test for cancer. It's a much less invasive kind of test that you can do. And we've got lots of data that we're using to try and to get this test working. But we're relying on the label that we get from the pathologist being the truth, right? So the pathologist says, yeah, this is cancer. So it's labeled with a 1 meaning cancer and 0 meaning not cancer, meaning normal. That's what we know. That's the thing we measure, or what the pathologist has given us. But it might not actually be the truth. And the reason for that is pathologist takes a sample. They take what's tissue, which is tumour, which is we're pretty sure they're right. They know what tumour looks like. And then they're asked to take another sample as close as possible to the tumour. So it's very similar in other ways. But of course, in that process of getting close to the tumour, by mistake, you might take a tumour cell instead, right? So you've confidently said this is not cancer, but you may have actually given me a cancer cell. So we're trying to figure out, can we actually figure out what the true label is? So Z is the unseen status, the thing we don't know. Can we figure it out? And so what this means in the language of probability is, can we estimate things like what's the probability that the label is 1? What's the probability the label says cancer, given that the sample is actually healthy? Right? And what's the probability that the label says normal, when in fact the observation is of cancer, the true state is cancer. And it's fun because my student's really smart. She's done something amazing. She's trained a whole, basically ChatGPT to read genes. So it reads genetic code, and it reads some other information as well. And you put it all in, and she trains it for days and days and days. And it comes out with a probability that we're looking at cancer. Of course, it's going to be totally fall over if we don't include this as well, right? So it doesn't matter how fancy your satellite is or how fancy your form of analysis is, you have to think about these kind of things even then, right? This measurement uncertainty. So I thought I'd throw that in there because I'm really pleased with what she's been able to achieve. But we have to solve this problem, right? Can we trust the data we've got? Also, the reason for including this is that it's an example of conditional probability. Okay, so we're going to come back to conditional probability quite soon. But there we go. Right. Okay, that's topic 1. Second topic now is propagating uncertainty. So we have uncertainty. What is that going to mean? And it's probably clear to all of you, I know, that if you're uncertain about your beginnings, you're going to be uncertain about your conclusions and your final discussion and your predictions. So that's something we have to take into account at all stages, right? Here I want to talk about something slightly different. What's the effect of new data? So if I get new data, what does that do to my level of uncertainty? So that's the kind of propagation of uncertainty I want to talk about today. Does it affect your measurement uncertainty? Probably not. Unless you can quantify how your device is working with new data, it probably won't change that too much. Model uncertainty doesn't necessarily change too much with new data, unless you decide that maybe some things you left out you can include now, or you've learnt something more that should go into the model from the new data. But it will certainly affect the estimates of your parameters, okay? And so I want to talk a little bit about Bayesian statistics here. So I'm happy to get into controversial stuff around this. It is controversial in some parts. I'm going to claim it's a natural framework for understanding how we propagate uncertainty when we have new information, new data. Okay. And here I'm going to grab a cosmologist quote. So that, again, this is how, without realizing it, I became a Bayesian early on, even before I became a statistician, because in cosmology it was really naturally, it was used all the time. Do I want to mention this, read this quote out to you? No, you can read it faster than I can say it. I want to always point out at the end, he says it has the advantage of higher efficiency and of a conceptual basis for dealing with the problem of induction in the presence of uncertainty. Okay, so that's sort of my theme as well. And I'm going to call this the Bayes way. It's kind of a secret knowledge. I don't know, is it taught in secondary schools? Is it alluded to at all? Or? No? Okay. So maybe we could riff on this for a little bit, because when I went through school, finding out stuff that wasn't being taught was really interesting to me. I don't know if your students feel the same way. I'm not saying you should quietly teach them Bayes on the side and stuff like that. But if someone is interested, you might want to push them in this direction. It's a bit like the Matrix, right? You have a choice of the red pill or the blue pill. You take the red pill, and you see the universe in a whole new light, right? That's the Bayes pill in this case, right? So yeah, just out of interest, I sort of thought it might be quite fun to sort of promulgate the secret knowledge around Bayes. So what is Bayes' rule? That's what hinges on this. And here I want to admit to something. I did my PhD in theoretical physics, and I very confidently told someone not long afterwards, oh yes, Bayes' rule best says the probability of theta given y is the same as the probability of y given theta. Absolutely confident. Because I'm a theoretical physicist, I'm way too confident. And I still remember to my dying shame realizing I was wrong, being told I was wrong. Yeah. So this is not what Bayes' rule is, right? These conditional probabilities are not the same thing. And this is the example I always give my students. If y means noises in the attic and theta means gremlins in the attic, then the probability of noises in the attic given their gremlins is probably close to 1. But the probability there are gremlins in the attic given their noises there is probably still close to 0, right? So that's why these things are not the same thing. But what it is the following thing. So I tell my students as well, I don't have any tattoos, but if I was to get a tattoo, it might be this formula. Just because it's really nice, and it highlights the thing I'm trying to tell you about, which is how we propagate uncertainty. P of theta is the probability of theta, so I'm using, in this case, theta to be a parameter of interest. So it might be how much dark energy there is in the universe. That's how much I have a belief about what this number is. That's my prior belief. Then I get some data, and I'm able to compute from that the probability of theta given y. So what data is y. I've made some observation. Based on that observation, what do I now think about this parameter theta? And that's encoded in this probability of theta given y. So given the data, now what do I think about theta? And that's called, in the parlance, the Bayesian update. Okay, so that's how we propagate uncertainty when we get new data. And science definitely has a Bayesian flavor. Certainly in cases like cosmology, where you're building on experiment after experiment, the posterior from one experiment becomes the prior for the next experiment. And so over time, we propagate uncertainty. In this case, the uncertainty often starts diminishing, right? Because we learn more and more, and our uncertainty becomes less and less. Okay. So back to cosmology, these things I showed you, that big orange ellipse, or part of the big orange ellipse, is actually a probability statement. It says, what's the probability for these two parameters given the data that the Planck satellite was able to obtain? It looks a bit like this. So where that's dark orange is where we think it's most likely, and when it gets faded out to lighter tones of orange, it's less likely to be out there. Okay. Obviously, you can see it doesn't constrain it very well, right? There's a very long, pointy ellipse. But as I was saying before, if you were to take what's in the blue as your prior, so based on these other experiments, I think it should be in this range, then given the data from the Planck satellite, I actually end up in a very nice, tiny spot in the middle here, right? So by accumulating the evidence like this, or the data like this, I can actually end up making very precise statements. And that's the magic of Bayesian statistics. Now, you can do it with other forms of statistics as well, but it's very nice, conceptually clean in Bayesian statistics. So that's how we can propagate uncertainty. Okay, how are we doing for time? Yeah. So if you indulge me, I'll talk a little bit about some work I have done. And I've taken that formulation of my colleague Andrew's into account. So what I want to do is take one of these, right? I want to drive up lots and lots of these, rows in an orchard, looking for these, and then construct maps like these to estimate parameters like these, okay? So maybe it's not as grand, it's not $1 billion quad bike, but it's something, right? And of course I didn't do it, someone else did it, they had all the fun. What they were doing is driving up all these rows and orchards, looking for disease. So here you'll see a disease tree on the left, this fruit which has become green, which has got disease. We can get a map of how that disease is spreading through this massive orchard. So this is a big commercial orchard in Florida. And then we can try to estimate things like how fast is that disease spreading. So on the x-axis, we're estimating how fast the disease spreads within blocks, and on the y-axis we have how fast the disease enters the block, basically. And what you're saying are this sort of cloud of points are posterior estimates for those parameters. So I had some idea beforehand what those parameters would be, and then I've given it some data, some of those maps like this, and be able to refine my estimates for those parameters. There's lots of clouds there. There's about 16 clouds or so, because there's one cloud for every block, basically. So I did a block-by-block analysis, and the color coding there is because the green blocks are really young trees, and the blue blocks are really old trees. And so you can see a really natural break and difference between the two blocks, how fast the disease spreads, and it has an age dependence. So that's something we could extract from the data, and something we could do during Bayesian statistics. Here's how the modelling framework looks like, trying to squeeze it into that framework I gave you at the start. We've got the thing we're looking at, which is orchards, changing over time. We have quad bikes driving around each time, generating maps of the disease, and from that we're able to estimate parameters. Very quickly, actually, do I have time? Maybe I just have time. To talk a little bit about the forward maps. This is where it gets quite interesting in the sense that you're trying to take other information from other people, like orchardists and plant scientists and so on, how we might implement this into statistics. This is how disease comes into a block. You have a little psyllid flying around, it's carrying bacteria. It lands on a tree which is otherwise perfectly healthy. In the process of eating from the leaf, it sends bacteria into the tree, which eventually becomes sick. And this bacteria multiplies and sort of it gets pumped around the vascular structure of the tree. So over time, this tree becomes infected. But it can also then generate a whole cycle of internal transmission or secondary transmission within the block. If an otherwise perfectly healthy psyllid comes along and lands on a tree which is sick, in the process of eating it will actually pick up some of the bacteria, and then it will fly off and land on a perfectly healthy tree and continue the process like that. So knowing all that's really important to figure out actually how that forward map looks like. And so we can look inside that forward map to have a tighter, sort of a more detailed view of what's going on. And I actually have quite a lot of fun with students talking about the kind of forward maps you can envisage. And often they get quite creative in thinking about this process. This is the one we settled on, where you have a tree which is susceptible, S, becomes exposed when the psyllid lands and starts eating on it. Eventually it becomes infected, infectious as well. And it can actually survive quite a long time without being obviously symptomatic. Finally it becomes symptomatic, which is D for detectable. And then at that point, often the orchardist will remove the tree because it's sick and going to spread more infection. So just think of these inside that forward map. This is the process which happens for each tree. So on the top, you've got one tree going through the process. On the bottom, you've got another tree, and it's being affected by that first tree. That just needs to be included. The observation model is actually really complicated because, as I said, we don't know the trees going through any of these states until we see it actually symptomatic. So we don't know about the E, I, and we only know about the D. And in fact, we only know the D when the person drives around on the quad bike, sees it. And that doesn't happen all the time. They go through every few months looking for sick trees. So we don't know precisely when it became symptomatic, but we have an interval. And then we know when the tree's been removed because we get told about that. So this is an example when you have measurement uncertainty because you actually don't see everything. So you have a partial observation. And so you still have to try and make predictions, and it turns out you can. And the Bayes leads the way, enables us to do that. And we can then take those estimates and we can think about future predictions about the course of the disease and what might happen if we try to control it, what might be the effect of controls we could put in place as well. And that's just to recap, that was the data. This is the estimates we could come up with for the parameters. And what was interesting, as I say, was just about this for the orchardists to sort of see how fast it was going to spread through the young trees. People weren't quite sure whether the psyllids would just spend most of their time in the old trees because there's many more leaves in a big tree, it's got more leaves to suckle, to eat, nibble on. But in fact, the young trees are much nicer because they're young trees, right? The leaves are more juicy, it turns out, right? So that's why they go to the young trees instead. Okay, last last topic, talking about evaluating uncertainty. So we've done including uncertainty, we've propagated uncertainty, now we're going to evaluate uncertainty. And this is what I led with on my abstract, this kind of question. This is not today's forecast, by the way, just in case you're worried. But will it rain or not is something which we think about quite a lot. I don't know about you, but when I think things like this, I go, at 2 o'clock, 10%. What does that mean? It probably means it's going to be just light drizzle, 40%, okay, maybe it's getting slightly heavier. That's not what it means, of course, but I still think that. It means that on 40% of times like this in Auckland, there was rain. That's, I think, what they really mean by these kind of statements. Anyway, so this is something you've seen a lot, I know, and that's what I want to talk about now. How do we evaluate this forecast, right? So at 3 o'clock, this is 3 a.m. actually, probably none of us are outside, but so at 6 a.m. we wake up and it's not raining. And the forecast said there's an 80% chance of rain. That doesn't sound like a great forecast, And that's what I mean by evaluating uncertainty. How do we evaluate a forecast once we see the thing that it was trying to predict? So this is a paper from 1950. I just love the fact that there was I think it still exists, the Monthly Weather Review. It must be a great journal. And it's more than just reviewing the weather, obviously. But its title was Verification of Forecasts Expressed in Terms of Probability, so the thing we've been talking about. And there's some great lines. I think the papers were way better back in those days. They were sort of punchier, got to the point, didn't muck about. There are a number of reasons why this problem has been so perplexing to meteorologists and others, but one of the most important difficulties seems to be in reaching an agreement on the specification of a scale of goodness for weather forecasts. So that's what this guy Breyer came up with. And he also realized that there was an importance in keeping people honest. So if you'll excuse the 1950s sort of language, the forecaster may often find themselves in the position of choosing to ignore the verification system or to let it do the forecasting for them by hedging or playing the system, in scare quotes, right? This may lead the forecaster to forecast something other than what they think will occur, for it's often easier to analyze the effect of different possible forecasts on the verification score than to analyze the weather situation. Okay. So I want to focus on this point. This may lead the forecaster to forecast something other than what they think will occur, right? And people still do that. In fact, sometimes for good reasons, right? If you listen to the radio forecast, they probably make things a little more doom and gloom than they actually are, right? Because no one wants to have a barbecue planned and it rains, right? They'd rather it was the other way around, right? It's going to rain today, and then it turns out to be nice. You go, great, it was, we got one back. So depending on where you get your forecasts from, they might not be honest with you. But what Breyer was trying to come up with was a system for encouraging people to give you their honest forecast, right? And then once they do that, we can evaluate to see how good their forecasts are. So what he was getting at was an idea of a scoring rule, and this is actually how I came into statistics originally. Maybe a little bit esoteric, but it does tie into statistics. But we use it to evaluate probabilistic predictions or forecasts. It doesn't have to be binary outcomes like rain or not. You're going to get rewarded for getting it right, but you're also going to, and you'll get a reward for being precise. So if you have a high degree of confidence, you'll do well. But it does mean that misplaced confidence will be penalised. So maybe you're thinking back to where we started, Eiffel Tower or Sky Tower, how confident are you about what your answer is? A proper scoring rule cannot be gamed, so you can't play the system. It doesn't really matter how the prediction was made. We just want you to make the prediction in the language of probability, and then we can evaluate your forecast. So just so you know, in my setup, the lower the score, the better. So it's like playing golf. We're trying to get a low score. Here's some notation. So I'm throwing in some bit of maths here. The key thing is that we need to specify what's going to happen in two cases, right? When the outcome y is 0 or when it's 1, and how that depends on what probability you quoted. So we're going to use Q for the quoted probability. So you say 80% chance of rain at 6 a.m., that's 0.8. If it doesn't rain, that means y is 0. If it does rain, it means that y is 1. And so to get your score, we need to be able to, as our job, as Breyer's job, is to give you two functions, right? One is what's your score going to be if it doesn't rain, 0, and you quote a Q. And then what's the score going to be if it does rain, so y is 1, and you quoted Q. Okay, so we need to come up with good choices for this. And what Breyer showed was there were some good ways to do this, ones that were going to make people honest, right? So there'll be no reason not to say what they truly believed about the outcome. So just thinking about what this might mean, if it doesn't rain, right, we would like Q to be low. So you should do well if Q is low, right? And if Q gets large, then you should start getting a worse score. So that first function should go up as Q gets larger, and conversely, that second function should probably go down as Q goes up. So you might think, well, that's good choices. Let's just make your score to be Q in the first case and 1 minus Q in the second case. That does the right kind of thing. But it turns out you can game the system. So I'm not going to go through the maths of this. It's one of the things you can do if you have insomnia one night. But your expected score will actually be lower if you don't tell the truth. Right? Okay, so this is kind of what I call the maths of honesty. I'm overloading the notation a little bit, but this function here, SPQ, is your expected score when you said P but quoted, or you believe P but quoted Q. So there's two things going on here: what you tell Briar, right, and what you believe, right. So P is what you believe, and Q is what you quote. And you can game the system if it turns out by saying one thing, you can do better than what you actually truly believe. Okay, so the Briar score, Briar showed how you could actually come up with a score which can't be gamed. This is just a little graphical depiction of what's going on. So in that black curve is the score you're going to get on average if you believe P and quote P, right? With that bad choice, or the choice that can be gamed, if you think that P is less than 0.5, then you should choose to be go on this red curve by quoting Q as 0. And that will always be beneath that black curve. If you think P is bigger than a half, then you jump onto the other curve over here and you say Q is 1, and over there you're always going to be underneath that black curve as well. Okay, so you're never saying what you truly believe, but you know how to game the system. Okay, so that's what the problem is, and what the problem that Brian actually solved with his scoring rule. Okay, let's jump to the final thing, and this is something I'm hoping you might take away with you to the classroom. I haven't used it a lot because in this setup it relies on a binary kind of outcome. So you have a test, a question, or exam question to say, which one is true or false, or choose A or B. So it's a multi-choice with two choices, right? So I'm going to flip things over and make, now we're going to make a large score a good score, right? Because students don't want to get low numbers. They want to get high scores. So we're just flipping the sign on this thing. But this is what's called the certainty-based marking scheme. So if your answer is correct and you've specified a low degree of certainty in your answer, you'll get 1 point, right? Because you kind of got the right answer, but you weren't super sure about it. If you had a medium degree of confidence, you get 2 points. And if a high degree of confidence, you get 3 points, which seems fair, right? However, if you got it wrong, then if you had a low degree of confidence, you'd just get nothing. If you expressed a medium degree of confidence in the wrong answer, you'd lose 2 points. And then remarkably, if you had a high degree of confidence to get it wrong, you get minus 6 points. So notice how your misplaced confidence gets really penalized. And you might think it's a bit weird. Why is it this way? This is actually set up this way so you're going to be honest. It turns out this will encourage honesty. You can't game the system. But most people need a calibration phase, right? Because it's a bit weird to be scored like this. And what you often find is people are super confident, really quickly get into a hole if you do a sequence of these true-false questions. They get minus 6. Yeah, I know for sure it's true, and then they're wrong. They lose 6 points. And they go, shoot, I've got to kind of catch up. I've got to try, now I've got to get 2 questions right to try and, to catch up, and so on. And so people need a little while to equilibrate and realize that the best thing to do is say what they truly believe. You can't game it. Don't try and be more confident than you are. Other people actually realize that they can be more confident than they are. Maybe they're actually more timid, right? Maybe they knew more than they thought. So it's actually quite interesting, and it'd be great to hear your feedback on whether you think this would work, or if you do implement it, how it does work. I think it's interesting kind of feedback to get. People have to recalibrate their confidence. And I guess the key ideas here, and this is maybe the main take-home, is that admitting to uncertainty is not a bad thing. And knowledge is knowing what you do know and also what you don't know. Okay, so we're almost done. How about we go back to that original question? Which is taller, the Eiffel Tower or the Sky Tower? How degree of confidence are you? Low, medium, or high? Okay. Okay. I've never ever had this experience before. Either you're so thrilled I've stopped talking, now you can talk yourselves, or this generated serious interest. Okay. Should we do a show of hands? Normally I don't make people do a show of hands, but should we do a show of hands? Okay, so let's start with just who thinks higher. Who thinks Eiffel Tower is taller? Okay. And so I guess everyone else thinks the Sky Tower is taller? Yeah? Okay. If you thought the Eiffel Tower was taller, how confident were you? Were there any high confident people?
Oh, this one there.
One there. Medium degree of confidence? Yeah. And low degree of confidence? Okay, so probably evenly split. Very few thought the Eiffel Tower. Okay, suppose those who thought the Sky Tower was the tallest, who had a low degree of confidence in that belief? Okay, medium confidence. And what about high? Okay. Probably even, I'm going to say that the people who had the high degree of confidence in the Sky Tower being taller were in the majority there. However, they were wrong. If you had a high degree of confidence that the Sky Tower was taller, you'd lose 6 points. So well done to the 2 people out there who got the maximum 3. Just to say something, if I'd asked you this question 2 years ago, it would have been different. So I had to check this out. The French, I don't know if it's something to do with the Olympics or whatever, but the French put an extra Sky Tower used to be 4 meters taller, and now it's 2 meters shorter. They put a little 6 meter thing on top. What's that? Yeah, I think so. I don't know, maybe not. Okay, so I hope you enjoyed that. That's how you can evaluate uncertainty. And as I say, I do think it provides valuable feedback for students. I'll leave the last word to Mark Twain. It ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so. But what's the probability he actually said that? I don't know. He said a lot of stuff on the internet. Anyway, thanks very much. Appreciate it.
I am going to think that, but
Do you want this?
But we actually do have time. If anyone has any questions for Matt, actually, put you on the spot. If anyone's got anything to ask Matt while we've got him here with us. Anyone at all? Yeah. Oh, yeah. Ben, yes?
Just the little blue blobs on that diagram.
Yeah.
Can you maybe explain them in a little bit more detail, how they were slightly separate?
These ones?
The lower blue blob on the left and the higher blue on the right. So they're old.
Yeah, so you probably can't quite see. Oops. Sorry.
So in your older trees,
Yeah.
can you explain the lower clump on the left and the higher clump?
Oh, okay, right. So yeah, this probably comes back to model uncertainty in the sense we don't know everything that's relevant. So these blocks that I looked at, I don't have a block picture. It's not quite, it's roughly, you can probably see some reasonably, so it looks like about 9 blocks, roughly. We're looking at blocks about that size, so several thousand trees. But we're not taking everything into account that's probably relevant, in the sense that some of the blocks are on the edge of the orchard, and some are in the middle of the orchard, so even if they're the same age, their characteristics are a bit different, so I think that's probably some of it. So what was interesting about this is that some of the, there was an orchard next door, which wasn't being treated, and had basically been abandoned, and so lots of the psyllids were thriving over there and then spilling over, right? So if you're an edge block, you're probably getting more external infection than you were if you were inside these orchards. So that's what I think is there. So that's a great example of model uncertainty, not including everything which is relevant, or not knowing to start with what might be relevant, and so not having it in the model.
Well, thank you so much, Matt. And you don't know, Matt, but actually who remembers the level 2 sampling activity with the orchards? Yeah, is it all what you were talking about was bringing back memories. It's an old task, but yes. Where the road was, where the river was. Yeah. But thank you so much, Matt. That was a really, really great talk. I like the 3 different ways of thinking about uncertainty and the real focus on modelling. And if you've been reading or looking ahead and kind of thinking what's coming down your way, there is going to be a focus on modelling and broadening how we do predictive modelling at the higher level, at curriculum level 7, level 8. So all of this is super relevant, and particularly thinking about how we score our predictions. Wasn't that great? Thinking about not just whether you got it correct or not, but also what your level of confidence is. That's so cool. So like you said, that you think, hopefully we'll take this back into the classroom. I can see us using that pretty quickly, actually. And even just on e-decisions, actually, asking them to say how confident they are at the same time as whether they get it correct or not would be fantastic. But thank you so much.